So I wanted to show you a piece the book went through that doesn't always make sense as you do it. So I'll try to show it to you with my drawings, and then we'll look at some simulation. Look at a simulation and show how it's trying to show the same thing. Okay. Try to think about the simplest bond we can put together. 2 hydrogen atoms. Okay? I want to take 2 hydrogen atoms and push them together. How do they bond? Well, let's think about the forces involved. First of all, they have nuclei. And the nuclei have the same charge, so the nuclei will repel each other. They don't want to be next to each other. That would stop the bond from forming. That's against it forming. But the electrons are attracted to their own nucleus and the nucleus of the other one. So we've got 2 counteracting forces. Okay, so we've got separate kind of forces. One trying to pull them together, one trying to push them apart. But they don't take place at the same time because the electrons and the nucleus are separate from each other. So as those electrons repel each other, got that in there too. The electrons don't want to be next to each other. So you put those 3 forces together, there's going to be some distance that has the lowest energy. As we push them closer, the attraction gets stronger and stronger between the electrons and the nuclei. But once they hit a certain distance, then the nuclei start repelling each other, so they won't, that you have to push them to get them closer together. Okay? That distance is called the bond length. And that lowest possible energy is the bond energy. That distance between them when they reach that lowest energy, that's how far apart they're going to stay, the length of the bond. So over here, where there's 2 atoms completely separate from each other, they have no energy. As I start pushing them closer together, they start sticking to each other a little bit better, sticking a little bit better, sticking a little bit better, and then they start repelling if I try to push them too close together. So where they have that lowest energy, that's the bond length. And right here, that lowest energy is the bond energy. That to separate those 2, you'd have to dig those 2 out of that hole. They reached a low energy point. Okay. So, unfortunately, that black never shows up well on the screen. But so if I take, so this is saying the same thing. Let's refresh this. So if I take a hydrogen, and as I push them together, They attract, they attract, they attract. See, the yellows are saying, ooh, they attract, they attract, they attract. And suddenly, there's no force, and they start repelling each other. Okay.
And would the yellow be their electrons attracted to?
The yellow is the force they're filling. It's the yellow what they're filling is the push or the pull. They're trying to show that with an arrow. And the bigger the arrow, the bigger the force.
Okay.
So it's a very little force when they're far away, but as they get closer, it becomes stronger and stronger and stronger and stronger until it reaches the maximum, and that's how you get that graph drawn. Okay? Now, if I try an oxygen and an oxygen, so I have to refresh it first. So it's oxygen and oxygen. They get bigger nuclei. As I push them together, it's the same effect, but it happens a lot further apart because oxygens are bigger. Does that make sense? Right? So that's what they mean by lowest energy. Okay? And that overlapping, that low energy comes from filling noble gas configurations. All right, electron dots is one way to show bonding. So is electron configurations. You can show bonding with electron configurations. It's a little harder to do because it's not as easy to write. Okay, so if I'm going to do the one for H2, the electron configuration for H is 1s1. Second was also going to be 1s1. So if they share these electrons, there's 2 in the 1s1 for each one of them. Because they both atoms get to count them. So if their outside energy looks filled, they both look like helium. Okay? And we would draw that as, hey, well, H has one dot. Another H has another dot. They both have noble gas configuration. Okay? So I prefer the dot method, but the configuration one, I got to show you the configuration one, which is the real one, has to work first. Right? We've been doing dots. We've got to make sure the real one works. Okay, that? What about F2? Fluorine's one of the diatomic molecules. Well, F is 1s2, 2s2, 2p5. So each F would be, in terms of orbital diagrams, 1s2, 2s2, 2p5. Would everybody see where they're going to be able to share those electrons? Those last two share, and you end up with noble gas configuration for both of them because they both get to count each other's electrons.
Wait, so how do they bond and share an orbital if like they're both the same spin?
We don't actually know what spin they are, and 50% are each way. So we just put them in up. We don't know that they're up.
But assuming they are both up.
They're both up. Those two probably would be less likely to interact because they'd have to change the spin of another one. Okay. Okay. O2 gets a little bit harder. So O2 is 1s2, 2s2, 2p4. Right? So there's my O's. That doesn't make them noble gas configuration. What do? Share more. They share both of those p electrons. They just have to share twice, right? So I'd have to make 2 bonds. I'd have to make a double bond. Okay, so if I did N2 at 2p3, each one of those to be missing, you'd have to make 3 bonds. Right? One bond isn't enough to make them happy. I got to do 2 bonds. And we call those 2 bonds together a double bond. So there are multiple bonds. A multiple bond is where they share more than one pair of valence electrons. So the ones we've done so far are single covalent bonds, a pair of dots. A double bond, or a double covalent bond, is when they share 2 pairs of electrons. And 2 pairs is 4 electrons. Anybody guess what the next line is going to say? Triple bond is when they share 3 pairs of electrons. Okay. Well, what do you think the next line says? There is no such thing as a quadruple bond. Okay, it is sterically hindered. There's not enough room for the electrons. Because think about this. We have just said we are going to put 6 pairs of electrons in the same place. Do you think they really can go in the same place? 6 electrons want to be together? No. So we got to find places for 6 electrons. Whoa. So the orbitals have to change. Hey, to give you an example of where this works. Carbon dioxide. Hey, the formula for carbon dioxide, carbon, 2 oxygens is carbon, 2 oxygens, CO2. Right now, I said I have to tell you. I really don't have to tell you. Eventually, we'll be able to figure it out. Most often, if you got 3 atoms, something's got to be in the middle, and it's usually the least electronegative, because it's more willing to share. The other way it would be is the one that can make the most bonds. Okay. So, CO2, that's my jigsaw puzzle. I've got C and O. Carbon has 4 valence electrons. Another important way to look at that is it has 4 holes. Wants 4 more. Oxygen has 6. Means it has 2 holes that needs filled. So those are my pieces. My jigsaw puzzle's got to look like CO2. So I put them together. Put together a C and an O. The carbon now has 5. The oxygen has 7. Neither one's happy yet. Carbon's still 3 short. Oxygen's still 1 short. So, but that's okay because I'm not done adding atoms yet. I have to add an oxygen. What's the second oxygen going to attach to? It's going to hook onto the carbon because we said carbon is central. So if you put oxygen on oxygen, then carbon wouldn't be central. Okay, so I put the second oxygen on. That solved my problems. No, actually, both my oxygens have 7. And my carbon only holds 6, only has 6. So now everybody looks like a noble gas. So sharing one pair of electrons was not enough. We tried it. It didn't work. The only solution is to share more. So I'm going to take one from each atom, move them in, erase them, and move them in. If you look at this oxygen over here, it gets to count all the electrons in the bond. How many electrons are next to or around that oxygen? 8, or 4 pairs. 1 pair, 2 pair, 3 pair, 4 pair. That's why I didn't separate you said don't pair them up till they have to. There's 4 pairs, 2 of them are in the bond. So it'll still be 4 pairs. Actually, this is just bookkeeping. We'll talk about where the electrons really are later. Okay. And if it worked on one side, work on the other. Okay. So this required, that's not the one I want. This required 2 double bonds. Just remember, each atom gets to count all the electrons in the bond. So that carbon has 8 valence electrons. The left-hand oxygen has 8 valence electrons. The right-hand one has 8 valence electrons. Is that right? Okay, let's try a few. PF3. P is group 5A, right below nitrogen, number 15. Molar mass 30.97. So phosphorus is in group 5A, it gets 5 dots. Fluorine is in group 7A, it gets 7 dots. So can you see where fluorine and phosphorus can hook together? Yeah, I can hook this fluorine here with its 1, 2, 3, 4, 5, 6, 7, and it's happy. The formula's not PF, so I got to keep adding F's. So a second one could come in here. 1, 2, 3, 4, 5, 6, 7. Hey, that fluorine's got 8 next to it. And one more F. See how we didn't have to figure out which one was the central atom? There was only places to hook F's on. That's what's going to happen most often. That is trifluorophosphorus, and I don't know what they would use it for. But I probably wouldn't want to be around it because fluorine things tend to be nasty. Because fluorine's got a really high electronegativity. CH2O. So I got a carbon with 4 dots, hydrogen with 1 and only needs 1 more, and oxygen with 6. Where should I start? Okay, so the oxygen and the carbon I should hook together because hydrogen's a dead end. It's one of the things we learned last week, right? Hydrogen's a dead end. So I'm going to put 1, 2, 3, 4, and then I can hook the oxygen with this 1, 2, 3, 4, 5, 6. Okay, so now I have to hook on hydrogens. I got my choices about where they go. Okay, I could put one on each of them. Okay, but to make the double bond, if I pulled that down and made that a double bond, that carbon would still only have 6 electrons. Said our secret to double bond was one had to come from each atom, right? So putting the hydrogens on one on carbon and one on hydrogen means I can't finish this, right? I do this, there's no way for me to finish it. So it was a bad choice to put this hydrogen over here. I should have put it here. Because now I could take this one and that one and bring them in and make myself a double bond. And that way, everybody gets to look like a noble gas. The oxygen has 8 next to it, 2 pairs in the bond, 2 pairs not in the bond. The carbon's got 4 bonded pair. Each hydrogen has a bonded pair. We see how we need. Why did we put a double bond there? Because we tried singles and it didn't work. Yeah.
Wait, which ones did you bring in?
Okay, so remember I had 1 left on carbon and 1 left on oxygen.
Oh.
Does that make sense? So there's 1 on each. That was why I had to put both hydrogens on the same carbon, was so I had 1 on each, so I could do that. Okay. So we're back to, it's jigsaw puzzle time, right? It really is a jigsaw puzzle. You know what it's got to look like when you're done. What pieces have to be hooked to which. Okay, what about N2? We said the nitrogen we breathe is diatomic. What do the molecules of N2 look like? How are they attached? Well, the first N gets 5 dots. The second end gets 5 dots. Bless you. Do I have noble gas configuration there? No, I don't have noble gas configuration there. So the only solution is to share more, right? So bring 1 pair in, 1 from each. Did that solve my problem? I took 1 from each. Yeah. Remember, we're just counting them. So I don't have 4 pairs there. So I must need another pair. That nitrogen's hooked together with a triple bond is the only way I can get everything to look like a noble gas. Because everybody gets to count all 6 electrons. They each have their own pair outside of the 6 bonded pair, the 6 bonded electrons. C2 does not happen in nature. No. Not stable. How about hydrazine? Rocket fuel. This is rocket fuel. Okay, so N2H4. I put my 5 dots for N. Do I want to fill this N up with H's? No. I'm going to have to hook the second N onto this. Okay. H4. Well, it's really handy that it came out to be H4. Because I got 4 hydrogens to stick on, right? And I got 4 places for them to stick. Everybody see what the 4 hydrogens will fit into this? H, H, H. And by doing that, every hydrogen has a pair of electrons next to it, right? And the nitrogen has 4 pairs of electrons. Well, got the same pieces. End with 5. I'm going to have to hook it to end with 5. Okay. What happens if I put both H's on the same end? I put that H there and that H there. Is there any way, I fixed that nitrogen, is there any way I can fix the other hydrogen? The other nitrogen? Say, well, you can make a double bond by moving those in, but that wouldn't work. Yeah, so it's like a jigsaw puzzle. Sometimes the first place you lay them down is not the right place. So erase them and take their dot with them. And then now I've got, just to annoy you, I'm going to do it this way. It doesn't matter where they come from. I know you want them all in a line, but we're not saying it's really in a line. Actually, it wouldn't be in a line. I know what shape it is. You'll be able to double shape either, and it's a 120-degree angle there. Eventually, you'll be able to get the shape. Okay, and one last one. After this one. Because if you knew how to name these, then you wouldn't make the mistake you're about to make right now. So, BA. What's it doing? Stop working. Okay, so I have another. So BA gets how many dots? 2. And CL gets 7. Everybody see how the BA and CL are going to fit together? No, you don't. Barium's a metal. It's going to give its electron to chlorine. And I'll need another chlorine. And it'll make Ba2 plus and 2 Cl minuses. The first decision is not, how do I build this? The first decision is, what kind of compound is this? One's a metal, one's a non-metal. They got to transfer electrons. The first thing we learned. Nonmetals and hydrogen share. Or just nonmetals, or nonmetals and hydrogen share. No, I am nice. No, mean would be putting that the first time you saw it was on the test. See, that would be mean. But I'm going to keep throwing those in there because that's the mistake. We get really good at doing one thing over and over again. But our first choice is to do that. Yeah, Peter. They can do both. So they can be both losers and gainers. So that's our. I will always make it clear which one they're doing. But actually, usually what happens is, if they're with a non-metal, they're usually losing. And if they're with a metal, they're usually gaining. Okay. All right, because you've seen it before and I don't want you surprised, you can indicate bonds with a line. But then, we really can't call it a dot diagram anymore. It's called a structural formula. It's the formula with structure added on top of it. What's hooked to what? It's still H2O, but now you know that the H's are both hooked to the O. H2O doesn't say that. Just remember that a line is 2 valence electrons. So I still got to be able to count 4 pairs of electrons. A line is a pair of electrons. So when I'm counting over here, I count the line as 1 pair, 2 pair, 3 pair, 4 pair. So that's what a single bond looks like. A single bond is one line connecting the two. Here's what a triple bond and a double bond look like. A triple bond is 3 lines. A double bond is 2 lines. Now, when we do dots for a triple bond, we do this. Okay. When we do lines, we make the lines 3 lines connecting. And we just got to make sure, hey, this carbon right here, it's got an octet of electrons, because 4 lines is 8 electrons. And this is what the structural of the CH2O you just drew as dots would look like. Although for some reason I drew it at bizarre angles. Okay. And then there's one last possibility of moving dots. That's called the coordinate covalent bond. Don't run into them very often, but they happen every once in a while. When one atom donates both electrons in the covalent bond. So we're still donating electrons to make a double bond or single bond, double bond, or triple bond. But both electrons come from the same atom. So in most cases, it's going to be one that already has an octet that you don't want to break up. So if you move the whole pair, you haven't changed the octet at all. Place where it shows up is in carbon monoxide. Okay, it's about that time of year. It's about time when we get our first couple of cold nights, you'll start to hear about people who die of carbon monoxide poisoning. Carbon monoxide is a colorless, odorless gas. Okay, it happens because you get incomplete combustion, and so if like a bird built a nest in someone's heater vent, exhaust vent over the summer, the exhaust can't go out, it comes back in. That's why they changed the law so that you have to have a carbon monoxide detector in your house. If you're a renter, they have to provide one, and if you sell a house, it has to come with one. Because the only way to detect it is with the detector. Symptoms, low level, it feels like the flu. I mean, if you just got a small leak and you're continuously exposed to it, it feels like you're sick for as long as you stay in the house. You get better when you walk out the door. Because what it does is it binds to oxygen better, it binds to red blood cells better than oxygen. So even though you're breathing oxygen, it can't get to where it needs to be because the red blood cells are hanging on to carbon monoxide. And so this time of year, people find out their heaters don't work, they bring their grill inside. Not a good idea. Colorless, odorless gas. Okay? So, now the formula for carbon monoxide, can you guess? Just a C and an O. Okay. Monoxide, carbon, 1 oxygen. So I stick the two of them together. Does that give me noble gas configuration? Carbon with its 4 dots, oxygen with its 6. So how did we solve this last time? Shared more electrons, right? So I take one from each. Now the oxygen has got the right number. But the carbon only has 6. So I've got to get more electrons onto the carbon without losing them from the oxygen. Okay, see, that's where I'm stuck at? I've got to get more electrons on the carbon without losing them from the oxygen. So oxygen still has to be able to count them. So I take a whole pair of electrons and share that. Now, that's going to give me a third pair for carbon. So I'm going to have to pair up those extra electrons too, so I end up with 4 pairs. So I move the whole pair in, but that's going to force me to take those lone ones on carbon. Now, you can see, because I color-coded where my dots came from, where the dots came from, right? That the oxygen donated more electrons to this than the carbon, because you've got 2 white ones and 4 yellow ones.
And then you had one on one side of the carbon and one on the other side. Did they just bond together
No, they just paired up.
for low?
Yeah. Okay. So let's go back. So moving this in gave me 3 pairs of electrons here. Right? I can only have 4 pairs of electrons. I can't have 3 pairs and 1 and 1. So all I did was just pair them up.
I thought they don't pair them.
Well, they do, but they have to because it's 4 pairs now. 1 pair, 2 pair, 3 pair, 4 pair. If I left them as separate, I wouldn't have 4 pairs of electrons.
So you have to.
For every that's the octet rule. Okay. Now, if you're drawing lines instead of dots, you take one of the lines and change it into an arrow. To show you which way it came from. Right? Can you see that the oxygen gave more electrons? So showing that whole pair came from the oxygen. How does it behave differently because it's coordinate covalent? It doesn't. It doesn't behave differently, but that's the only way you can form them. Okay? But okay with this? So that's what your homework's going to have you do tonight. Draw some dot diagrams, talk about multiple bonds. Okay? Tomorrow we'll practice some more of this. Didn't realize it was jigsaw puzzle day, right?